My name is Dante DeVry, and for our senior project, we work together.
My name is Eddie Flores.
My name is Armando Martinez.
Our senior project is the Effects Management System, or FXMS. It's a system designed for effects pedals, for managing effects pedals aimed at guitarists. Effects pedals are basically DC circuits that affect an AC signal on its way to being amplified. There are many different varieties of effects pedals available today on the market, but they have various limitations.
One of the problems with the analog pedals is that for musicians, a lot of them, they have like not only 3, 4, a lot of them have like 10, maybe a whole set of 10 pedals. And one of the problems is to actually rearranging all the effects pedals, as you see on the picture, right? They're connected in a chain series. But let's say if I wanna place the first pedal in the third position, I will have to actually unplug the cables, and probably I will have to turn off my amplifier. Otherwise, you will hear like a pop. And on stage, you don't really want those things, and especially for very professional musicians. So that's one of the main problems, to be able to rearrange all of these pedals in different positions. They are in the market. They are actually digitalized pedals. They have many effects, but they actually do A to D conversions, and they cost a lot of money depending on the quality. And but nowadays, a lot of musicians, they still like to buy the single effect pedals, and they want to be able to use them. So like I mentioned before, the main problem is to actually rearrange them. So the solution to this problem, we actually created a system that the musicians can actually plug in all of their single effect pedals, and our system can actually automatically rearrange them in different orders internally. Also, the musician can actually set and also recall any presets that has been saved into the system. And we have also motorized the pedals, because some of the pedals have actually knobs, so the musician, this actually lets the musician control them automatically by just recalling them.
Here's a block diagram of how our system works. The blue line, the darker blue line, is the AC signal from the guitar. It goes through the routing system, and our microcontroller sends data first to the motors to control any of the knobs that have motors hooked up to them, and then depending on the data it sends to the routing system, the chips that we have that we'll discuss, it may send the AC signal through loops through these pedals, and then out to an amplifier.
How are used for our project? We was mainly the microcontroller. We also have some jobs for connections, plugging the guitar to our system. We definitely needed a stepper motor, for precision purposes, to locate whatever setting that we may save or recall to do. Of course, also we need our sound amplifier. Additionally, for the routing system, there were another multiprocessor that we needed for, as I mentioned before, the stepper motor basically would drive the pedals effects knobs. We also need some drivers, since we have additional motors. We could not use the driver that was embedded into the driver board. And our microprocessor basically controls the motors, routing and preserving navigation, as well as recording previous settings.
Alright, so I'm going to show you our product design. So as you can see, we're actually using the Dragon board. This is the routing circuit, and we have the 23 pedals for now, and they're being controlled by motors, the knobs. Here's another view. And this is actually the Dragon board. So in the LCD, it actually, M1 and M2, it refers to the motors. So and the values is actually, it goes from 0 to 40. It's turning the knob from left to right. And the two numbers in the middle actually represent the settings, in which settings you're actually recalling. In this case, we made it so so that you have chapters and then pages. That's the way we wanted to show it. And here we have one of the pedals being motorized, and this is the routing circuit. And this is the schematic. So we're using multiplexers. So each multiplexer is actually taking 2 bits, and that actually in each multiplexer assigns the position of the pedal. So the first chip assigns which pedal gets to be in the first position. The second chip assigns the second position, and the third chip assigns the third position. And depending on the values that you send to the chips, you could actually rearrange the order of the pedals. And here we have the motors. It's sitting basically on top of the pedals, on the knobs.
As we mentioned before, because the reason they're using the motor driver was because Dragon Board basically does not provide enough current to it. So this is just a diagram how we interface it to the motor, selecting some pins to enable each motor, as well as inputs and outputs.
The code we wrote in C. We used ImageCraft IDE. We wrote in that and used that to compile it. Here's a flowchart of basically what our program does. It pulls all the buttons that we have, checks if there's anything pressed, if there's any button pressed. If not, it just displays on the 7 segment. If there are, it checks if it's a motor button pressed. If it's not a motor button, it updates the route based on what button was pressed. If it was a motor button pressed, it updates the motors based on the motors pressed. And then what we always have to do is display on the 7 segment because it's a multiplex display, otherwise it'll go blank. So our code will break down into 3 sections really quick, and we won't go into too much depth. But the first part deals with signal routing. So again, from what Eddie presented, I want to focus on the select bits going to the chips. And we used 6 bits in a variable called route that was encoded like this. Preset navigation, we broke down an array of 16 elements into 5 groups of 3 with 1 element that was a standby element. We also introduced 2 other arrays of motors, and this is where we save the settings and recall the settings for all the different presets that are available to the musician. We use the same element in the array count to get the same place in the array of the configs array and the motor A and motor B array. We also developed an algorithm so that we could navigate through the array, both by page, which would be 1 by 1 here, and then we call these different chapters. This is chapter 1, 2, and 3, and we were able to navigate by chapter, also going to the first element in the next chapter or the first element in the previous chapter. And motor control.
For the motor control, basically we're going to use the keypad, which is embedded in our Dragon Board. Most of the time it's going to be 4, and depending on each key, whether or not it's pressed, it will either increase the button or a specific pedal, decrease it, as well as save and record it. This is the subroutine for the increase volume. Basically, what we do is just monitor each position at each step of the motor, and then we use a full step method in order to get certain definition to it. And in the value, we just select each coil of the motor and shift it. Either one will go to the left, to the right, which we will change the direction of the motor. As well as we mentioned, this is our subroutine. It basically works the same as the decrease. It just depends on the direction of the motor is going to. Clockwise or clockwise. One of the main features is to record the value. So since we did not use encoder, originally we wanted to use an optical encoder, but due to the high cost, we decided just to monitor each step of the motor. By doing that, we just create two arrays, and independent each position, and then we will subtract each position. For instance, let's say position 0, position 1. One will store the current value, that specific motor, and position 2, it will just basically store the save, or whatever value was at the time that you saved it. Then when we record it, we just take the difference between both of them, whether one gives us a negative or positive, so we'll just call our increase or decrease function. Here we just have, we need to mention, in order to get determine the position of the motor, so we just send specific values to each of the coils. So that what we have here our driving motor, which is called the ACM 75410, and we just give under two inputs. Also we get our outputs, and we determine the position of the motor to drive. This is a full description of how to trace those the specific position of the coils. We just use it for illustration purposes. We use that full step.
Yeah, we're going to skip through the in-depth description of how it works, and we're kind of going to show you how it works instead of telling you. So we can leave the name up there next. What? So we'll wrap up the presentation part.
One of the problems during a project, sometimes we, regardless of how well planned we make, we often encounter the problem. Also we worry about our failure as well as obtaining the specific hardware. Additionally, we also have we worry about our functions. Our continuous implant was basically intensive testing. We all are placing orders in advance, and we spend a great deal of testing and debugging. And we try to work within our projected estimated cost. So we just try to, we get additional step motor, and we debug pretty much a lot.
So far, what we have is just that we have the circuit built already, all the connections with the stepper motors. We also did some more testing. We had some problems in the beginning, but then we fixed them, as Amanda was saying. And basically, everything is actually running pretty well. So that's our present status. We're actually set. So in the future, other additions that we wanted to include is actually making it wireless, doing some wireless settings. So then our system could just be like on the side, and maybe if the musician wants to have many more pedals, they could actually get another system, and actually the systems can actually communicate with themselves, identifying how many pedals are connected. So then the musician can actually navigate through his pre-settings, wirelessly on stage. So those are some of the additions that we had in mind. Yeah. Okay.
So I just want to go over responsibilities real quick. I was somewhat of a project manager. I designed some of the front end and the software. Eddie built the chip and the prototype and researched the hardware. Armando did a lot with the motors. The motors are all Armando's work, basically, and the software for the motors as well. And we'd like to thank our faculty, And thank you, everyone. We had some help from a couple companies that gave us parts for testing purposes, for educational purposes. So thank you, everyone.
Let's hear the music.
Oh, you take requests?
Actually, here is it.
Okay, so right now everything is in bypass. The pedals are connected. So now this will be pedal A, B, and C. So now I'm just gonna activate pedal A. And I'm gonna add some distortion. And I'm actually gonna switch them. You could hear the difference. I'm gonna do it again. Now I'm gonna add pedal C into the chain. And as you can see, you can hear the differences. And now, if you could actually take a look at the motors, I'm actually gonna rotate them. So right now we're just controlling this first motor going up, and you can see the values increasing. The motor rotating, now decreasing. Again, I'm gonna control the second pedal. Go back to just hear the acoustic guitar. I just put everything on standby. Okay, so now no effects are being included. Now I'm gonna record some pre-settings. So this is already saved in the system. Now let's say I just wanna mess with the motors. If I want to go back to my settings, the way they were before, all I have to do is just press this button, and you're gonna see the motors rotate automatically to their previous position. Yeah. So this one turn back. Again, I'm gonna demonstrate. So I set them to value of 40, both motors. I don't wanna. I want my the previous settings, so I'll go back to it. So, and that's basically it. I mean, you could also save the settings if you like. So this will be on edit mode, and let's say I wanna have this. So the way it's set up right now is pedal B, A, and then C, and from there it goes straight to the amp. So now I wanna save it. I just press the mode button again, and let's say I could also, and if I want to go back to my settings, there you go, BAC. I just recall whatever I said before. That's about it.
Beautiful. Any questions? Anybody has?
How many settings that you can save for those?
Right now, one setting?
No, how many settings that you can save?
16 settings.
16. And how do you select between either one?
To see between them. I mean, when you actually want to edit, you can actually see them here and navigating. You just set the settings with these 3 buttons. You could just control them. Like this is for pedal A, B, and C. So if you press, you're actually gonna see there's some changes. Right now, I'm kind of like shifting A, So now it's going to be in the third position, and then if I don't want to include it, I press it again, and it goes to bypass.
Then you can save that setting and we
And I could save that.
It's
setting,
like a
yes.
4-bit setting, or 16.
How come I didn't see you press those?
Well, see, that's another thing. On stage, let's say if I don't want to use this pedal, you know, I mean, if I'm in another place and I want to just shut this off, I will have to come back to that place and press it. But if I have the already, let's say, a wireless setting, I could just do it from far away and not hear it.
Actually, Professor, we're not turning these effects on and off. They're on all the time, just routing it through them in different order.
You can bypass them as well, so they won't be
I see. Yeah, that was the question. All right, good.
Very good, gentlemen. Excellent. Good job. All right, we have one last group. The